The Burj Khalifa rises more than 2,700 feet into the air. By the normal rules of physics, getting water all the way to the top should be nearly impossible. At that height, gravity is constantly fighting against you. Yet every day, people on the highest floors turn on a faucet and water comes out as if nothing unusual is happening. What's even stranger is that the solution isn't one giant system powerful enough to force water to the top. It's something far more complicated, and understanding that solution reveals a much bigger story hidden inside the world's tallest building. Because the Burj Khalifa isn't really a skyscraper. It's a city standing upright, a vertical city made of steel, concrete, glass, pipes, cables, pumps, elevators, and mechanical systems stretching nearly half a mile into the sky. From the ground, the tower looks almost impossible, like something humanity pushed beyond its natural limits, and in many ways, it did. The problem is that everything humans know about building cities assumes one thing. The ground is flat, water networks spread across neighborhoods, sewage systems flow beneath streets, power lines travel from one district to another, transportation systems move people horizontally from place to place. Almost every urban system ever created was designed to expand outward, not upward. But the moment you try stacking an entire city into a single tower, those familiar systems begin behaving in unfamiliar ways. Gravity becomes a constant obstacle. Water doesn't naturally climb hundreds of floors into the sky. Force it upward too aggressively, and the pressure can become destructive. Pipes can fail. Equipment can break. A simple plumbing system suddenly becomes a major engineering problem. Then there are the elevators. In a normal building, an elevator is just a convenience. In a structure this tall, elevators become a transportation network. Thousands of residents, workers, hotel guests, visitors, and maintenance crews must move efficiently through the tower every day. Without careful planning, people could spend enormous amounts of time simply traveling between floors. And then there's the desert itself. Outside, Dubai's summer temperatures can reach around 122 degrees Fahrenheit. The tower's massive glass exterior is constantly exposed to intense sunlight and heat. At this scale, cooling isn't just about comfort, it's about keeping the building livable. A traditional city spreads across the landscape. The Burj Khalifa stacks that city into the sky. And that single change turns nearly every rule of urban engineering upside down. The higher the building climbs, the more difficult every system becomes. Which brings us back to the first challenge engineers had to solve: water. The Burj Khalifa uses 249,908 gallons of water every single day, pushed through 62 miles of pipe. That number sounds impressive until you do the math on what it actually takes to move water upward against gravity through a building that is 828 meters tall. In a normal building, one pump at the base creates enough pressure to push water to a rooftop tank, and gravity distributes it downward from there. That works fine at 10 floors, at 20, even at 40. But the moment you try to push water all the way from the basement to floor 163 of the Burj Khalifa in one continuous pressurized run, the physics turns hostile in a way that ends with structural damage. If a single pump tried to push 946,000 liters of water from the basement to the 163rd floor, the pressure at the base would reach 1,200 pounds per square inch. For reference, the water pressure at a standard household tap runs at around 50 pounds per square inch. A firefighting hose operates at roughly 150 pounds per square inch. At 1,200 pounds per square inch, you are not dealing with plumbing anymore. You are dealing with a hydraulic cutting tool. Engineers created a system that pumps water to a series of tanks at different levels throughout the building, housed on 7 two-story mechanical floors staggered throughout the structure. Distributed around every 30 stories, these mechanical floors house electrical substations, water tanks, pumps, and air handling units. Water travels 30 floors, stops, fills an intermediate tank, resets to zero pressure, and a new pump picks it up for the next 30 floors. 6 water transfer sets and 7 pressure booster sets equipped with hydrovar variable speed drives handle the full load. reducing energy consumption by 30%, while maintaining constant residual pressure at any outlet regardless of the time of day or the number of users simultaneously drawing water. Each zone is an independent pressure circuit. What happens in Zone 3 cannot cascade into Zone 4. The consequence without staged zones is not hypothetical. It is mechanical certainty. The tower also features 132 miles of pipe for its fire emergency system and 21 miles of chilled water piping supporting air conditioning. Every one of those miles of pipe depends on the same staged pressure logic. A single pump failure in a monolithic system at floor 80 does not just cut water to the upper floors. It takes the fire suppression system offline simultaneously. It floods the electrical substations on the same mechanical floor. It kills the pumps that supply the cooling system. Water, fire safety, and climate control all share the same pressure architecture, which means one wrong calculation in the water system would have brought down 3 others with it on the same day. The remaining question is not whether humanity can build taller than 828 meters. It is how hard we are willing to fight to get a glass of water to the 300th floor. The Burj Khalifa proved it was possible to build a vertical city in a desert and keep 35,000 people alive inside it every day. The systems that make it work, invisible behind the glass, behind the walls, behind the mechanical floors that most occupants never see, are the real achievement. And in approximately 2028, every one of those decisions will have to be made again, harder, higher, and with less margin for error than ever before.